A spherical, non-rotating planet has a radius r and a uniform density ρ throughout its volume. Suppose that a narrow tunnel were drilled through the planet along one of its diameters, as shown in the figure above, in which a small ball of mass m could move freely under the influence of gravity. Let r be the distance of the ball from the center of the planet. Part A. Show the magnitude of the force on the ball at a distance r less than big R from the center of the planet is given by F equals minus CR, where C is a constant equal to 4/3 pi g rho m. We're going to take advantage of what are called the Newtonian shell theorems, which is that for a spherical collection of mass, the only stuff that matters for gravity is the stuff closer to the center than you are. So we're going to take our image, and we're going to say, let's draw some smaller sphere R. I'm going to say when we're that little distance out, all that matters is the stuff in that sphere. And the stuff further out doesn't matter because it all cancels out. So we just need to figure out, if we knew that mass, then we'd be in good shape, because we'd say, oh, then the force is just g times the enclosed mass times little mass over r squared. But we need to find the enclosed mass, but that's not too bad, because the enclosed mass is just the density times the volume that's enclosed. The density is given, and the volume of a sphere of radius little r is 4/3 pi r. 4/3 pi r cubed. So we put this back over in the other one, and we say this is g times rho 4/3 pi r cubed times little mass talking about over r square. And then we can say, oh, well, then some stuff goes away. Most especially r cubed over r squared is just r. And so we get g 4/3 pi rho r m. And I suppose, strictly speaking, the way that they like to do it, they would say the force should be negative because it's attractive. And we look up here and we say, well, obviously the thing we just wrote, we have our minus sign. And then we have, well, we can pull out everything but the r, and we would have 4/3. There's a pi, there's a g, there's a rho, and there's a little m. So we get to say QED. We showed what was asked for. On the axes below, sketch the force F on the ball as a function of distance r from the center of the planet. Well, we can say that when we're inside the planet, we have the one they just told us, minus CR, for r less than r. And when we're outside the planet, we have something like g mass of the planet times little mass over r squared. And that's for r bigger than r. We can actually clean this up a little bit, because we know that the mass of the planet would be rho times the volume of the planet. So rho times 4/3 pi big R cubed. And so we can think of this instead. Let's get rid of this. And now we can say that it's going to be minus g times 4 pi thirds rho r cubed m over r squared. And the key thing here being it's an over r squared bit, whereas here this is linear. So we would expect that the force kind of becomes increasingly negative here, and then falls off, and this is going to be a little tricky to get. If I go twice as far away, I should be 1/4. So let's try and do that a little better. So by the time I get here, I should be something. Sorry, sketching is not that easy on this device, but something that looks like 1 over r squared, something like that. And of course, asymptotic, not crossing the axis. So they're looking for something that looks in that general vicinity. I didn't really prove it, maybe you should, that they would meet here, but they'd better meet here. And we can see that if we put little r equals big R into our expression, they do meet there, so that's good. The ball is dropped into the tunnel from rest at point P on the planet's surface. C, determine the work done by gravity as the ball moves from the surface to the center of the planet. And there's actually several ways to do this. We can do it analytically. We could do an integral of the work, and we could say, I'm going to do it I have a little weird way of doing it. I know that the work done, the infinitesimal little bit of work done, is the force dotted into the displacement. The problem is I like to have my displacements be that the x is increasing. So I'm going to compute the work done to go from the center to the surface, which I'm going to call work outward bound. And I know it's going to have to be the integral of dw. So it's going to be the integral from 0 to big R of the force. But hey, we figured out what the force was. It was minus CR dotted into dx, which is just dr. And so we're going to get minus C integral from 0 to big R of R dr minus C integrating big 0 to R of R dr is R squared over 2 from 0 to R. So we get minus 1/2 C R squared minus 1/2 C 0 squared, or minus 1/2 C R squared. But that was the work that would take to get out. My actual work is minus that because it's going the other way. So it's minus 1/2 CR square, or 1/2 CR square. For completeness, we shouldn't use C, so we'd have 1/2 of, and remember that C was given as 4/3 pi G rho m times R square, which concludes at 2/3 pi G rho m R square. Maybe you're not a fan of doing integrals. We can still do what I said before, that the work out is the integral of f dr. And if we look at this way, that work is going to be, well, the force looks like this. This is F versus R. And you remember that that means that the work is the area out to some distance trapped by the integral. But that's easy because, hey, this is a right triangle. So the area is just 1/2 base times height. The base is R. I guess it's now capital R because we're going out to capital R. And the height is the force at that point, which, as we said before, would be G times the enclosed mass times a little mass over R square. So we have 1 over R here, Gm, and the enclosed mass would be 4/3 pi big R cubed times rho. And we see again that all of this stuff, oh, and there's a minus sign because, of course, the force here is negative. So we again get, when all this is said and done, we get 2/3 pi G rho m R squared. Of course, I should be careful as I'm doing all this. There was that minus sign, which means the actual work we're looking for is minus the outward bound work, which is minus 2/3 pi G rho m R square. But maybe you don't like using work as an integral at all, even if it's easy to compute because it's the area of a triangle. Well, then I've got something else for you. Remember that we were given that the force law is minus some constant times R, which looks an awful lot, right? Which is like that the force is minus some constant times x. So yes, this is in fact just a harmonic oscillator. It's a little weird to think of it because it's a planet-sized oscillator with a weird mass at the end, but we can treat it as an oscillator because it has a force law that is a restorative force with a constant times the displacement. And we know that the work in stretching a spring is 1/2 kx squared, or for this case, 1/2 c r squared. And at max, that would be 1/2, well, the work done, the spring does negative work. And so we get c capital R squared to stretch it outward. And again, our inward bound force is the other. The work the spring does in contracting back after being stretched is the positive version. And so we get this times our constant, which was 4/3 pi g rho m times r squared, or again 2/3 pi g rho m r squared. So there you have 3 different ways to answer part C, all of which are perfectly acceptable, and approach the problem from slightly different points of view. Determine the speed of the ball when it reaches the center of the planet. We could do this through the work energy theorem, which tells us that delta K is the work done. And so we can say 1/2 mvf squared minus 1/2 mv initial squared, which was 0, equals the work done, which is 1/2 cr squared. And so we can we can obviously get rid of this bit, and we're left with that vf is, let's see, the 2's cancel, and we have square root of cr squared over m, or r times the root of c over m, which maybe you want to plug in or not. The rubric says you can leave it, so feel free to leave it. But if you don't want to leave it, you could put the 4/3 g rho m all over m, and we get square root of 4/3 g rho all times r. Or you could do this by energy conservation, which will look basically the same way, because you would have the energy at the start equals the energy at the end. The energy at the start was 1/2 cr squared. The energy at the end, of course, is 1/2 mvf squared. And now we're in the same place, so we really can just solve it the same way. All right, so they asked us what happens when this thing, oops, that's a pretty bad circle. That's still a bad circle. What happens when the thing has fallen to the center of the planet? And describe its subsequent motion. Well, it's moving, but it's reached a point where there's no force, so it no longer accelerates. Instead, it rises back towards the surface, but getting slower. And then at the surface, it will come to rest, and then it will repeat the motion, accelerating towards the center, but getting less and less acceleration, having none here, and then accelerating backwards so as to slow and go here. This is a place where it really does pay off to have just recognized that it executes simple harmonic motion with no damping. All right, it just goes back and forth and back and forth and back and forth. Allegedly forever, right? In the standard meaning of forever for physics, which is until something else happens. Notice that we've neglected that the planet's spinning, so this would be a little weirder if you had to include the planet's spin. You'd have to have the tunnel wouldn't go straight down. Otherwise, the thing would run into the walls of the tunnel. So it'd have to be like some weird logistic curve curving it out. But they didn't want that. So we can just say it just bounces back and forth from time to time. People have, by the way, proposed something like this for getting across distances really fast, and we'll see why when we do part F. Write an equation that could be used to solve the time it takes the ball to move from point P to the center of the planet. It is not necessary to solve this equation. Cannot stress that enough, that in a test situation, you probably shouldn't. You don't have time. It's interesting because they often will say, do not solve this equation. Here they're saying you don't have to solve the equation, and that's a little bit of a freedom. When they say do not solve the equation, they mean do not solve the equation. But here we're fine not to. The actual solution is, in my opinion, a little goofy, but they're like, well, what they really want you to do is to say that F net equals ma. So in this case, they're both accelerating in the same direction, so I can say just CR, and of course A is d squared r dt squared, and that's all they're looking for. I mean, it's only worth a point, so they're not looking for you to do a lot, but it's really a little bit more interesting if you're like, but wait, this is an oscillator. So couldn't I instead say, hey, the period of an oscillator is 2 pi square root m over the constant, which for us would be 2 pi square root m over that c they gave us. And of course we should be able to do that. So if we plug this in and we say t is 2 pi root m over 4/3 pi rho pi g rho m, whoops. And then we notice the mass cancels, so maybe we do something, I don't know, I would probably not simplify the thing here, but we might say something like 3 over 4 pi g rho. This is very much a case where we need to be careful not to be seduced by having done something interesting and forget that it's not what was asked for. We weren't asked for the period, we were asked for the time to get to point to the center, but that would be 1/4 of the period, right? Because the thing falls back and forth in one period, and that's 1/4 period, 2/4 period, 3/4 period, and then back. So we need to go over here and say it's, what is that, pi over 2 root 3 over 4 pi g rho. And I don't know, do we simplify this? Sure, I suppose. Root 3 pi on the top, a 4 on the bottom, and then nothing else you can do than 1 over root g rho. And the only thing that's interesting is that if you take the density of the Earth, which is about 5,000 kilograms per meter cubed, although it's not really constant, then on Earth this becomes just about 22 minutes. It takes about 22 minutes to fall from the surface of the Earth to the center of the Earth under these very bad assumptions.